So now we have 6 in the session. Bilal and Vina is not here. Okay, we proceed with our example, right? Okay, so just now we seen the MOM equation, moment of momentum equation, and then 2 more equation, which is in question 34, right? These two. Then let's look at the application. So question 35 will be a bit lengthy. So you need to prepare an extra paper for the answer. All right. Now this is a sprinkle system, as you see on question 35. So the water enter the rotating sprinkle through the base. So again, it will be the same exact setting with question 7, not mistaken. Question 12 in your tutorial is the same setting. 1000 ml per second. Acid area is given, which is here. Section 2, area is given, 30 mm square. Flow flowing from each nozzle is in tensional direction. Radius is given. Radius from center is 200 mm. So again, be careful on the conversion of unit later on. All right, ml have to change to meter cube. Mm change to square. Mm change to meter. All right. So what are the strategies to solve, right? So there are 3 instructions here. One is the resisting torque. Second one also torque. The third one is a speed of sprinkle if no torque. Right. The first one is stationary, do not move. Second one with a certain speed, 500 revolution per minute. And the third one is without torque. So let's see how we apply the moment of momentum equation in this question. So if we compare to question 12 is more on a linear equation. So this one is on the moment of equation. All right, we will start referring to the diagram and some understanding that we have. So in the diagram that you have on your tutorial paper, you have the dash red line there. So this is the control volume, or this is our focus area to solve the question, right? And we only focus on axial torque to analyze as a resistant motion. So we need to calculate the T shaft, right? T shaft, if you look at here, we have R and force here coming out here. So we need to calculate the torque from the nozzle acid here, all right? So yeah, make some marking in the diagram. So this is focus area for the nozzle head, for the sprinkle head. So you have V1 from bottom, V1 absolute velocity in section 1, which is here. So mark your diagram. So at the center here is your section 1, section 2. So V1 at the center, and the direction is going in and is in the Z direction, going up. And you have your V2 absolute velocity, V2 at your axis area here. So section 2, section 3 is the same. So 2 V2 equal to theta 2. V2 at section 3 also same. This is V3, or V3 equal to V2, same. It's same because the area is the same, distance is the same. Right, the setting of the arm here is the same, so you have the same velocity. So add these 3 components in the diagram that you have here. So the first one, you add in the absolute velocity component. You have 1 and 2 here. All right. And recall the equation for your shaft. the torque for the shaft. Torque, again, torque is a moment, force times distance. All right. So in this case, we use distance, velocity, and mass flow rate. So because the in and out is the same, the continuity equation is applied here. So means there's no loss of your mass flow. So your m dot is positive. And the R and V here is negative because the direction of your rotational motion and the direction of your flow is different. That's why it's negative, right? So you have to understand why we have a negative here, right? This is just a remark. Our control volume is non-deforming, fixed, and our flow is in the tensional direction. So that's why we can put V2 equal to V delta 2. Mean we look at as a plane movement, X and Y plane, or X and R plane. Right. Right now, from this, the same setting, if you refer to question 12 in the tutorial, we already defined that the velocity come out from this side. Our V2 is 0.7 meter per second. So how to get this answer, you need to refer back to this tutorial 12. So we're going to not going to look at V2 again. All right. So yeah. So our V2, just in your answer there, you just make a remark there, refer back to question 12 in the tutorial on how you get 16.7 meter per second. So there's a calculation there, so the calculation steps still the same. The answer for V2 is 7 meter per second. So we have our V delta 2 component already. We need to find m dot. How to find m dot? M dot equal to rho AV again. And in this question, we are given the Q. So remember AV, A times the velocity. We get our Q, mass flow rate. In this case, mass flow rate is 1000 ml per second. You need to convert this one into meter cube per second. All right. So this is a calculation. This is a sample calculation. All right. So in later slide, most of the time I will just skip these steps. So this is just to show you how you substitute the answer. Focus of this answer is that be careful on the unit that you use. You need to do conversion, right? So rho for the water is 999. If you forget this one, you can refer to table 1.8. That is given in chapter 1 tutorial. So rho water standard is 999 or 1000. If you forget, you can just straight away use 1000. All right. And rho, this one, the area, Q is Q times V. Straight away, we already have the Q in the statement. It is 1000 ml per second. So change ml to meter cube means we change the ml into liter because we know that 1 liter equal to 1000 meter cube. Means you change ml to liter, divide the 1000, and it will become liter per second. So 1 liter equal to 1000 meter cube. So change this ml from liter, from ml to liter, then change to meter cube. All right, you do the conversion, you will get 0.999 kilogram per second. Again, maximum 3 decimal place for this module. Minimum 2 decimal place. All right. So even if you use 1000 here, your answer, you should give me 1.00 kilogram per second. Don't just write 1 kilogram per second. Minimum decimal place is 2 for answer. right? So we have the M here for the T shaft, top of the shaft. We have M already, we have V2. R2 is given. Again, be careful on the unit. R2 is in mm. So you substitute all the value, you get the torque from the shaft, right? Torque of the shaft because of the water flow. All right. So this is just a reference answer. You get a negative. Torque of the shaft, you get negative 3 point something, and the unit is Newton meter. Again, remember the unit of the torque. Torque is force times distance, or moment equal to force times distance. Force unit is Newton. Distance in meter. So be careful on the unit when you define your answer. Negative is because the work is done by the water that we explained in the previous slide. Right. All right. So maybe in the test you'll be asked to explain why there is a negative sign in your answer. If you have a negative sign in the answer, right? You need to explain why there's a negative sign there. All right, so this is just, we already done the section 1 to calculate the resistance torque. When the sprinkler head is stationary, it means we don't have movement on the arm.
Sure.
Yeah.
It's always negative, right? Because always the flow is
You mean
always
R? You mean R, is it?
Yeah.
R component cannot be negative. It's a constant. You measure, it's a positive value always. It's only that the negative here is because okay, let me show you the slide. You get a negative. Yeah, because of the direction of the flow. There's a slide just now, this one. Just now I explained why there's a negative here. Because if you look at the diagram, V2 is our flow, float flow, spray out from the head here. Direction is this way. However, when the water spray out, we know that our arm will be moved anti-clockwise. So we get a negative sign here.
So meaning like for every application, it has to be negative, since when it is switched on, it will always move the opposite direction.
Correct.
To the water.
Correct. Yeah, correct. Your statement is correct. In the reality application, yes, you will get negative, but you will have a positive when you have some mechanism that make the movement forward. Means there will be some design that make the arm swing forward as you spray water. In the normal sprinkle head application, yes, you get a negative. But there's a mechanism that makes the U2 become parallel to the V1. In the engineering application, you can make some mechanism that divert your flow or
It
make
is
the
the
arm.
U2 is the direction.
No, U2 is the reaction force. You can see as a reaction force when you eject some fluid from the arm. U2 is the reference velocity given by R times your omega. Do I explain your question?
Yeah.
Okay, yeah. So this one will follow your omega. Yeah. Right. So again, we have our T shaft equal to negative 3.4. Okay, so again, now we look at B. What happens if we have a constant speed rotating at a constant speed? Means we have omega case now. We have our omega already. All right. So just now we don't have omega, we don't have W, because there's a resisting force, means we jam the head here. So we calculate the torque. That's why we get the value for the resisting force. Now we want to find what happens if you let the head loose and the head rotate with 5,000 revolution per minute. And this diagram you can find actually the same as what you see in under question 33 in your tutorial. The one that you see in under question 33, that one is in 2D, but this one is in 3D. It's the same, right? So in this case, for section B, we will assume that the flow field is steady in average. All right. And there are some components that we need to look at here. Now we have additional component, which is our omega here, rotational speed here, radian per second or revolution per second. And then we have a W component here. Just now we only look at V and U, but now we have one more component which is called W. We have the complete vector relationship here. Right? V equal to W plus U. So we need to balance the force. Right? So recall what is the relationship between these three vectors. V equal to W plus U. All right, in this case, if you write V2 equal to W2 plus U2. This is the blue color equation. This one is a general equation. Apply between absolute, relative, and the reference. So in this case, we apply this general equation into section 2 head here. That's why you see it.
Master, do you consider the directions of U2 and V2?
You mean direction? Yeah, so in this case, we write out the equation first. So we only look at the magnitude in this case, because this vector relationship, this is fixed already. In this equation here, we only look at the magnitude, because the direction we already draw in a diagram here. So and then we link with general equation. Meaning we assume W2 is in this direction, U2 this direction, V2 is this direction. So you do the calculation based on general equation here. Then you see what happened to your answer. So if you get a positive, means you are correct. Means your assumption is correct.
Oh, I thought it's gonna be like V equals to either like
this is fixed already. This V equal to W plus U fixed already.
okay.
Yeah. So and then this is based on our logic, based on our rational estimation. You know that V2 is your this direction. U2 is the reaction force from the arm. So it will be in this direction, anti-clockwise, as you spray out water. W2, this one is the relative velocity. This one, we will always look at the water, the float motion. So in this case, we assume is follow the float direction. Okay.
So the absolute velocity and the relative velocity is the same also.
We assume. In this case, we
Oh,
assume. Yeah.
okay.
Yeah. Because W2 we know that is a relative. So relative means it refer to something, refer to a certain location. Even you sit here or you sit here, how will your velocity look like? It will still follow the float direction. The float will still spray out like that. So it's still a relative to any position that you look at. So it's still in this direction. In the logic way. Huh? All right. Now in this case, um, 2 we know that is absolute. So W2 we also find, I think in previous W2 is given. Right. If not, then you need to refer to tutorial question 12. So we have our W equal to 16.7 also. U2 just now. Where's our U2? U2 is 16.7. Right. Now U2, how we calculate based on R times omega. U2 equal to R2 omega. R2 is given. Omega is given. Revolution per minute. Again, change this one to revolution per second. So, and then 1 revolution equal to 2 pi. You need to change to radian. All right. You'll get your U2, V2, sorry, V2. V2 equal to 6.2 meter per second. So there's a change of identity of velocity here. So in the first case where there's no rotational, we know that our V2 is 16.7. But when our rotational, when our sprinkle head rotate at a 500 revolution per minute, our V2 component just now, the magnitude will transfer to W2. Then we need to calculate what is our V2. It will be a different scenario. Huh? So when the head is not moving, then we can straight away calculate our V2 just now compared to tutorial question 12. However, when we have a rotational motion, then we have a angular motion already. So you need to call out this direction, and then W2 will follow our magnitude in V2. It becomes 16.7 meter per second. And then U2 calculate from this equation, U equal to RW. You substitute into this equation here. All right. Then you get your V2 component. So these are the difference between moving and non-moving when we looking at the torque component. Okay. Just take a note now. So there's a difference when it's moving and not moving. Okay. And you can calculate your T shaft because you need to calculate your torque. Equation for torque is given by this one just now. Torque of the shaft equal to negative R2V 2 times your m dot. M dot you already given. So you just substitute the V2 just now. Once you calculate your V2, 6.2 You substitute into the equation, you get the torque is negative 1.24 Newton per meter. So you can see when it's not moving and moving, the torque is have a different value. So if you fix the head there, the torque is negative 3.3. And you let the head rotate at 500 revolution per minute, your torque drop to negative 1.42. Meaning if you let the head spin, your the float do not need to do more work lah. Means less work need to do by the float itself. Right. So this is the meaning lah, negative. Right? Okay, section C. What happens if there's no resisting torque? Means it's no friction, free to move. Right, when there's no resisting torque, a maximum constant speed of rotation will happen. Means this component W omega here will be maximum. So we'll use back these three equation. T shaft equal to negative RV times the m dot. V equal to W plus U. This is the vector equation. And then your U2 equal to R2 omega. Right. This is just a simplification of these three equations. T shaft equal to substitute the V2. Right. So again, in this case, we need to calculate the V2. What we do modification is that we substitute, we use this equation, and we use W2 as our, we substitute this one in. So V2 equal to VW plus U. So that's why you have W2 here. You know that U equal to R omega. All right. So we use this equation, substitute in the shaft equation there. Right. So there's no resisting torque. When there's no resisting torque, means on the left hand side, the torque component equal to 0. Means there's no torque or no friction or frictionless movement. There's no resisting torque. There's a yeah. All right. There's no resisting torque. You arrive at this equation. Then we need to get the omega W. So means you rearrange this equation, you substitute all the known value. Then again, this is the reference value. Sometimes I did a wrong calculation, but this is the way we solve question. This important is you know the strategy in solving problem. You get an omega equal to 797 revolution per minute. And then sometimes the question will ask you input in the radian per second and so on. So this is a general answer, just for you to check whether you're in the correct direction. Okay, so I think we have complete the application of MOM equation. So this is just a additional question. So what happened to the angular momentum when there's no resisting torque? So meaning that when no resisting torque, mean your torque component equal to 0, the water at the entrance, which is here, and out, will have a 0 angular momentum. meaning if you don't have resisting torque, angular momentum. He just explained what is the relationship between angular momentum and the torque. When there's no torque, no resisting torque, means you don't have angular momentum. Okay, we start to move into the third section, which is we start to look at first law of thermodynamics. We have clear for moment of torque, this one. Okay, let me stop this recording before we move to the next one.